In this session, I'm going to talk about how we can use the decision trees for counting related data. So counting is basically like generally number of hospital visits, right? Where we talk about number of, or I try to look at number of occurrences, number of defaults in a particular year for a bank loans, right? Or number of successes. So wherever I have such kind of scenarios to be determined, where I have to do the counting based on a set of attributes. Based on a set of attributes, I am creating a tree model to partition the data, and based on that partitioning, I am looking at number of occurrences of the response variable. So those are the situations where we can use the models which are more and more specific for counting data. Here I am going to talk about two such kind of models. One is the Poisson decision tree. The other one is the Poisson model based recursive partitioning. These are the two models which are heavily used. If my response variable, simple point is my response variable is a counting related variable, number of occurrences, right? Number of, here the example that I am taking is number of visits to a hospital. I want to really model how many times a person will make a visit to a hospital based on the various attributes associated with that person. Now for that, a small data set has been captured. Let me just load that data set and let me explain that to you. So this is the data set hospital. If I look at the size of this data set, the DIM, it says there are 4,400 rows and 13 columns in this data set. And looking at the first few elements of this data set, this talks about the number of visits to a doctor. So this is what I want to model. So in the first case, there are 5 visits, 1 visit, 13 visits. I want to see whether I can model the number of visits to a doctor based on the various other variables. Depending on the number of times he got into emergency situations, depending on how many hospital stays the person had till date, what is the health status of the person, average, poor, good, etc. Then number of chronic conditions that that person had, which is mentioned as 2, 4 something, the age of the person, the gender, whether the person is married or not, his education status, number of years of education he has gone through, his family income, then whether he is employed or not still, and does he have a private insurance for health, and does he have a Medicaid policy. So based on that, I would like to understand if any one or more of these various variables are going to influence how many times a person is going to visit to a doctor. That's the data that we are going to look at, right? And if we are looking at the structure of the same, we see that the doctor visits is an integer. All these are integers. Health status is factor with 3 levels: average, excellent, and poor. These are the 3 stages here. Chronic conditions, it's an integer. Age is an integer. Gender is a factor, male and female. Married is a factor with no and s. Years of education, it's again an integer. Family income is a numeric value. Employed, yes, no. Private insurance, yes, no. Medicaid, yes, no. And if I quickly look at the summary of this to do a basic understanding, so doctor visits, yes, it has ranged anywhere from 0 to 89. It's so big a difference. Emergencies 0 to 12. Hospital stays again is a number from 0 to 8. Health status looks like 3,500 people approximately have an average health status, whereas 343 of them have excellent and 554 of them have poor. Coming to the chronic condition 0 to 8, age 66 to 109. Wow, so elderly people are also there in the data. Gender 2600 females and 1700 males in the data. 2000 unmarried people, whereas 2400 married people are there in the data. Years of education going all the way from 0, almost uneducated, to 18. Family income, I don't know why it is negative, right? Probably there could be more of debts compared to any kind of incomes. Maximum is going to 54, might be an outlier. So 3,900 people are not employed, only 455 of them are employed. Private insurance, 985 of them don't have, whereas 3,400 of them have private insurance. And the Medicaid, probably 400 of them have the Medicaid with them. So this is what is the data all about. Almost all the variables are looking decent enough. All the categorical variables, the representation is decent enough. There is no variable where very little representation is there from the categories. Alright, now here we are ready enough to execute these two models, Poisson decision tree as well as the Poisson model based recursive partitioning on this data set. Now, Poisson decision tree, it's a decision tree where the objective is for a count response variable. Wherever my response variable is a counting related one, and we assume that it follows a Poisson distribution. So it's basically like number of hospital visits, right? If I make an assumption that the number of hospital visits follow a Poisson distribution with a mean that depends on the covariates, right? So which means for each of the subgroups, the response variable follows a Poisson distribution with a different mean. If it follows a mean for the entire set of data, then we'll have one single mean. But for different subgroups of data based on different covariates, if the response variable has a different mean values, then we can rely on the Poisson decision tree model. Even the Poisson decision tree is very well implemented using the rpart package and the rpart function. We have seen during the survival decision tree models, also we have used the rpart package, but there the method that we have used was exp. So if we use the method exp, it takes it as a survival variable, whereas if I am using the method as Poisson, it would be taken as a Poisson decision tree model. So the Z is the data frame containing the Poisson distributed response variable. So in this example, I'll take the number of doctor visits as the Poisson distributed response variable, right? So I have a data frame containing the Poisson distributed response variable, and I also have a data set of attributes which are used to build the tree. So with that, we can get started with the Poisson decision tree process. Initially, I have loaded the rpart package, right? So let me load it. I have loaded the rpart package. Get the data for which the decision tree need to be built. We have already got it. Preliminary inspection of the data is already performed. Check for NA values. We have already done, right? So there are no NAs as a part of the data. Now if required, you have to perform some kind of transformations. If I want to bring in some kind of logarithms where some of the response variables are the explanatory variables, better apply those transformations to the data. The response variable should be a count variable. So that's where I'm relying on the number of doctor visits, which is a count based response variable. Now, let me try going ahead in terms of building the tree for this purpose. If required, let me split the data. Right, it's also better that I split the data into training and the testing data. So let me say n, which is n row of hospital, number of rows, let me count. So it is around 4406. So I'll take it 4406 into approximately 70%, 3084. So what I'll do is I'll take a train which is a sample between 1 to n, wherein I will consider some randomly 3084 values with a replace equal to false. So based on that, I will build my training data, which is nothing but a subset of the hospital containing train rows and all the columns. Whereas my testing data will contain from the same hospital minus train rows and all the columns. So I have my training data and the testing data separated. In both the cases, the response variable is a count variable, which is the doc underscore visits. Now I have to build a formula out here. So let me create a formula wherein my decision variable is, my response variable is doc visits. Probably I can take everything. So if I have some kind of, okay, I will see how many emergencies will they influence, how many times a person visits a doctor, number of hospital stays, will they impact, the health status of the person, is it going to impact, number of chronic conditions the person is having, is it going to impact, or the age of the person, is it going to impact the number of doctor visits, the gender of the person, males versus the females, the marital status, is it going to impact, the number of years of education, is it going to impact the number of times you visit a doctor, the family income, right? People who are poor don't visit much, people who are rich, they are going to visit more. Is it something like that? Does the current employment status or having some other private insurance or Medicaid kind of stuff, are they really going to influence a person visiting the hospital? Now this is what I want to really see. So I'll call it as fit Poisson decision tree. Right, I'm calling it as fit poise, where I will use the function rpart. The formula I can directly now specify it as f. The data for me in this case is train data. I'll fit it only with the train data. So the data I'll take it as train data, and the method I will set it as Poisson. I'll set the method as Poisson. Now this is the model that has been fitted. If you want to check what is there as a part of the model, you type fit poise. So there is a kind of a splitting that is happening, which means we have done some good job. Chronic conditions less than 1.5. That's the first layer of split. Right now, if you see what has come as a part of the split. So first initially we have the node number. So node number 2. The split is chronic conditions less than 1.5. So having 1 or 0 chronic conditions. There are 1795 people from the training data who have less than 1795, who have less than 1 chronic, less than 1.5 chronic conditions, means either 0 or 1. Whereas the other side of the tree says greater than or equal to 1.5. So 2 and above, there are 1200 people. And what it says is the deviance here is 9700, and the y value, here the y value is the count. Approximately they have visited the doctor 4.4 times. Whereas if people are having more than two or more chronic conditions, on an average they have visited 7.68 times. So the number of doctor visits is very much dependent on the number of chronic conditions. And even for that less than 1.5 chronic conditions, there is again a breakdown. Number of hospital stays less than 0.5, which means approximately 0, no hospital stay at all. For them, the number of doctor visits is only 3.93. But for people who have stayed at least one day in the hospital, it looked like 7.64 is the on an average number of visits to the hospital, number of visits to the doctor. The same logic on the other side. For people who has hospital stays greater than zero point 0.5, which is 1 and more, it looks like almost 10 times they are visiting the doctor. So out of all those, so many things associated with gender, marital status, right, family income, probably none of them are getting as a part of this tree. That's one interesting observation. The demographics of the person are not playing any kind of an important role in terms of talking about number of visits the person is making to a hospital. Majorly the focus is on number of chronic conditions the person is having and number of times he has stayed in the hospital before. These two important features are driving whether a person is going to visit a hospital or not. Now based on this, I can do a plotting of the tree. So I can very well say plot of this fit poise. I'm plotting this Poisson tree. This is how it is coming out. And probably I can even represent the text here. So I'll take the text of fit poise. Let me just bring out how many observations are there. So that's the reason I'm saying use dot n equal to true, so that I'll get the number of observations. And just to make sure that size is slightly smaller, I'll try to put it as 5.5 or something. So 50% of the original size. So now you could see out here chronic condition, the same thing is represented in a graphical form, right? So you could see 6.65 here, 10.16 here, 7.67 here. So this whatever is there as a part of our textual part as a part of the model output is shown in a plot format. So that's one thing. So at every node, if I really want to see the number of observations and the number of observations and the number of events, I can also put all equal to true in the same thing. Right after doing the plot, I can also add for every node if I want, right, the whole details to be printed, then I can very well set all equal to true, so that for every node I will get total number of events, total number of observations, so that my understanding of each and every node could be more and more clear. And here also it's only a breakdown of the tree only to two layers. So there might not be much of a chance to get into the pruning of the tree, right? But yes, let's see. Right now, initially I have fitted the decision tree. I have used the plot and the text methods to visualize the fitted tree. We have done that. Each terminal node reports the event rate, right? In each terminal node, we are getting the events rate. How many of them? The total number of events and total number of observations for that particular node. So we are talking about the total number of observations for that particular node and the total number of events that are occurring at that particular node. Events are nothing but how many times people have visited the hospital. So on an average it is like 10.16 occurrences out here. Here it is 6.65 occurrences approximately. 912 observations are there out here. 377 observations are there out here. And overall 3832 visits have been made, making it on an average the number of visits equal to 10.16 and so on. So that's how you can do the computation part, right? Then, so if I really want for each and every node this kind of a breakup, I can very well put all equal to true in my text function before displaying the text. Now there is one more additional thing that I can do to this model, the print CP, which will take care of the validation of the decision tree, which will tell me whether the pruning of the tree is anywhere required. And this is more and more applicable if the size of the tree is too large. So it will tell me what is the optimal size of the tree. There is a CP value that is computed, and based on that, CP is nothing but complexity parameter. So there is a CP value that is computed, and based on that complexity parameter value, wherever the CP value is the lowest, that is what is an indication of the optimality of the size of the tree, right? So what we can try is, we'll try print CP simply. We'll use this function print CP for our model, which is fit points, right? I mean, let me tell you, this is more and more important only if your model is too complex, so many branches that are there as a part of the model. But for simple models like this, which have only 2 layers, there is no dependency. I really don't need to go with this step, but just that if you want at a later point, you should be comfortable with. Now you could see here some of the things. The first thing is the formula that you have used, the variables that are actually used in the construction of the tree, the number of chronic conditions and the number of hospital stays, only 2 things. The error at the root node is around 6.13. That is the error because there are total of 3084 observations which are there as a part of the training model, and 18,927 telling me that the root node error is approximately 6.13. And there is a split, right? You see there are 4 layers that are going out. So let's talk about each one of them. First, initially there is a formula used to fit the tree, the variables used to build the tree. The root node error in this case is around 6.13. Number of events at the root node. So you could see the number of events that are there at the root node, which is what is resulting in the root node error of 6.13. Relative error, cross validation error. So different kinds of, and finally the way the CP is computed at each of the layers. So we are talking of n equal to 1, 2, 3, 4, the different splits that have happened. 0 split, 1 split, 2 split, 3 split, the node at the split. Then we are talking about the relative error slightly coming down, the X error is again slightly coming down, the standard error is also on the downward path. Now what we really look at is, we can very well do the plotting of the same. Each row represents, if I have to interpret what are these 1, 2, 3, 4, each row represents the different height of the tree. If the height of the tree is 1, right, this is what is the CP value, number of splits, relative error and so on. Then again, if the CP is, if the number of splits is 2, number of splits is 3. So it is talking about different height of the tree. More the levels that are there as a part of the tree, the classification error would come down. Right? If there are more levels, obviously the classification errors are going to come down, but there is a risk of overfitting. So the way we typically look at our level is where the relative error plus a standard is lesser than the X error. So relative error plus X standard 1.04, it is greater than X error. 0.92 plus 0.04, it's greater. 0.89 plus 0.03. So you can choose the lowest level where relative error plus X standard is lesser than X error. So that could be the kind of a ballpark that we can very well choose, or prune the tree so that it has the minimum X error. So here the minimum X error is coming out here. So I can very well prune the tree to this kind of layers. And if you really want to go into the plotting of the same, you can very well use the plot CP function. Plot CP function of the Poisson is telling you that the CP is coming down as the size of the tree is actually increasing. 1, 2, 3, 4, the size of the tree is increasing, the relative error is actually coming down drastically. So wherever the relative error or the CP value is the lowest, that is where we can think of going ahead with the size of with that particular size of the tree. And now we can very well go ahead in terms of the summary of the fitted tree. We can very well get into the summary of the fitted tree, which can give me various stages or steps in which the whole process has got carried out. But most importantly, so this is how the variable importance has been looked at as part of the whole tree. 47% importance going to chronic conditions, 37% going towards hospital stays. There is an 8% scenario going into emergencies, 7% into hospital status, and 1% into whether the person is having Medicaid or not. So because the whole process of doing the tree, different kinds, different steps that are being taken intermittently is giving me this whole effect of variable importance. Right, so you could see that in some cases Medicaid is being used while doing the whole process, and that is what is the final observation for us. Right, you could see the mean deviance of this much, all these things coming out at each of the different nodes. Now, if possible, I can also take this information to do the prediction, Poisson. Right, I can very well do the Poisson, where I can do the predict. The model is Poisson, and I want to do it on the test data. So the Poisson is the prediction that I have done on the test data. Now let me see what has gone as a part of the Poisson. I've got approximately how many visits that each of these people are going to make. Right? I'm getting approximately how many visits each of these people are going to make. I can very well compare them. Right? I can do a correlation between the Poisson and the actuals, which comes from test data dollar doc underscore visits squared. So there is something test data. Let me look at the names of the test data so that I can see if I have given some. Doc underscore visits is the not in the caps, it's in the small letters. Okay, doc underscore visit squared. Oh, so the model is giving me only a correlation of 7%, the R squared of 7%, the number of visits. Okay, to this extent it came out good enough, but finally when I'm trying to project it with respect to my actuals, it's not coming out that comfortably, right? With the training data, the model came out slightly better, but when I have applied it on the testing data, giving a number of visits the person is going to make on an average, it's not coming out that appropriately when we are using the correlation part, right? So there is a problem. This is on an average the number of visits the person is going to make. In some cases the numbers would have been much higher, some of cases the numbers would have been much lower. But let's see the correlation, at least from the perspective, if not uh, the method, if I take it as Spearman, would there be any kind of an improvement in the correlation? Yeah, almost 31% correlated. The Spearman is looking much better compared to a Pearson correlation, right? At least who will spend more, who will come for more visits, who will come for less visits is coming out through this Spearman. Or even when I give a Kendall, yeah, more or less 25%. So compared to a Pearson, these correlations are looking slightly much better because these are more in terms of at least highlighting who will visit more versus who will visit less. But yeah, it's better that I get a few more important details before I progress in terms of applying this model for the further prediction purposes, right? So here I got the variable importance when I did the summary, and I also got the details of the terminal nodes. Each of the nodes, how many observations, how many events, right? You could see here for each of the nodes before this. Node number 4, 1570 observations, 1681 events, 1681 visits to the hospital, estimated rate 3.93, and the mean deviance of the same is around 5.01. So there is a deviance, right? So that's how the whole splitting up has happened at node 4, node 5, node 6 and node 7, right? Alright. So now let's move forward to understand the same model, trying it a little bit differently using Poisson model based recursive partitioning, right? Probably let's see by using the recursive partitioning if something can be improved. But the objective remains the same, the data remains the same, everything is similar. So we are going ahead with the party package with the mop function. So I'll go with a library of the party. I'm loading the party package, right? So here I need a Z, which is a Poisson distributed random variable, which is more of a count related variable. XYZ are the regression covariates which are used as a part of the formula, whereas ABC are the covariates which are used for the partitioning. In a recursive partitioning model, we have seen that there are two types of covariates that we use. One, which are primarily targeted for building the model, and two, which are targeted towards splitting of the data. So here also we will take that kind of a step where a few of the variables will be used for building the model and a few of them will be used for partitioning the data. Right, all these things are fine. We have loaded the package, we got the data, we have done the preliminary inspections, all this part is taken care of, right? So here identify which variables are conditioning variables and which variables would be used for the splitting purpose. So what I would like to do is the two which I have got, the hospital, number of chronic conditions and number of hospital stays. Those two I want to use for building the model, and all others I want to take them as the covariates for splitting or partitioning the data. So from that perspective I am developing the model. right? I need the variables for the development of the model. Okay, so I'll take it as doc visits is my response variable. I'll take number of emergencies plus hospital stays plus health status. No, chronic conditions. I'll take them as inputs. Right, probably I'll take one more. Family income also, let me take it as a variable. But the conditioning or the partitioning I would do on all the remaining variables. Health status, right? Age, I want to do the partitioning based on the age of the person, gender of the person. I can use them as a part of the model building as well. The marital status, number of years of education the person has, the family income I have taken as a part of the model building, whether the person is employed or not, and the person has a private insurance or not, and a person having the Medicaid or not. So these are the ones I'll take as a part of the partitioning variables, whereas only 3 of them I'll take as a part of the model building variables, right? So this is what I'll take as a formula. Now let me try my fit, and this is typically called as Poisson model based recursive partitioning. So I'll call it as party, because I'm using a party package, I'll call it as fit party. Now I'll use a function mob, wherein the formula is f. The data for me is train data, and the model in this case, if you remember the mob function, I have to specify the model. So in this case, the model I'll still give it as the linear model, whereas the family I will set it as Poisson. Right, in case of logic based recursive partitioning and probit based recursive partitioning, we have used it the family as binomial, and here I will set the link function as the log. That is what is an indication of the Poisson. Right, I will set it as log. The link is log is what I will give for this particular Poisson model based recursive partitioning. Okay, so there is a model that has been built. So let me see why these warnings have come out. Family is disregarded. Why is the family disregarded? Okay. Okay, I require covariates here. So that could be the reason. Fair enough. Let's see what comes out. Right. So let me type in fit party to see whether the model has been executed or not. Yeah, it is executed. So initially it has taken health status average excellent, and the other branch is health status is poor. So that's a kind of a branching that has happened. For health status poor, it directly became a terminal node, and this is the kind of a model that came out for the health status being poor. But for health status is either average or excellent. Again, one more thing that came out is private insurance being no or S. So for people having private insurance, a separate model came out. For people who don't have a private insurance, another model has came out. So for people who don't have private insurance, this is how the doctor's number of visits to the doctor has come out. But for people who have private insurance, again, years of education mattered in this case. Less than 17 versus greater than or equal greater than 17. So this is how the whole split of the tree has occurred. and if required I can very well monitor this model. I can even look at the plot of this model fit party. Okay, I have to give it in small letters. Okay, so this is the plot of the model. So you could see number of visits ranging in a different way altogether for each of the branches. You are getting the number of visits based on all the four parameters that you have considered. Right, the four parameters that we have considered are emergencies, hospital stays, chronic conditions, family income. I could see with the emergencies nothing much, right? Probably looking like slightly increased with the number of emergencies, but here there's not too much of a difference that is coming up, right? And similarly, you can very well look at each and every aspect like this. If there is a kind of an increase or a decrease significantly, so for these kind of graph, it's always better that the number of variables that we are considering are much lesser. So overall, I can look at the coefficient of the entire model. So I can very well consider this all together as a part of the coefficients. So I'll call coefficients of fit party. So this is how the formula is coming out, 2.1. So if whichever is falling into node 3 is something where the private insurance is not existing. So for them, the number of visits is typically coming out as 2.1 plus 0.48 times emergencies plus 0.13 times number of hospital stays plus 1.46 times the number of chronic conditions minus 0.124 times the family income. So that's how the whole thing is coming out. And if required, if I want to compare it with some other models, I can very well compute the log likelihood of the same. So the log likelihood of the fit party is this much, and for any model to be better than this, I want the log likelihood of it to be higher than this. Similarly, the AIC also is something that I can very well look at, and because AIC is more like a representation of the error, I want the AIC to be lesser than this. And I can very well look at the stability of each of the parameters for any given node, right? For node 3, node 5, I can very well assess the stability of the parameters for each of the nodes using the p-value. I could see whether the parameter values are, so these are the parameter values, node 3, node 4, node 6, node 7 for each of the headings. I want to see whether each of them are significant or insignificant. So this is what I can test using the SC test. SC test is primarily the stability related test associated with each of the parameters. So I can simply say fit party and I can give the node number. So if I say node 3 and I look at the SC test, it says so here the p value is 0.99, so insignificant. Age 0.99, insignificant. Probably I could see all the variables are insignificant out here, right? So whatever are the coefficients that I have got for node 3, almost all the coefficients are really insignificant for me. Similarly, if I want to test it for node 5, node 5 also looks pretty much insignificant. Almost all the variables are looking insignificant for me. Node 6, the same story is continuing. So we are seeing that majority of the variables, whatever are the coefficients that are being talked of, there is a lot of insignificance that is associated with the variables going with this method. Now I can very well use this method for the fitting purposes. I can do an estimation of the data, right? So we have fitted the tree on the training data, get the coefficients, estimates at the leaf nodes which we have got, log likelihood and all we have used for comparisons, SC test we have used to look at the stability of the coefficients at each of the nodes. Then we can go ahead using the predict part, right? So I'll say pred underscore or pred underscore party is nothing but I'll use the predict function. Fit party is the name of the model, and I'm using it on the test data. So if you look at the pred underscore party, the output that I'm getting is the number of visits each of these people are going to make to the hospital. So I can very well find out the correlation between the test data dollar doc underscore visits, which is the actual data, versus spread underscore party, which is the predicted data. So the correlation comes out to 0.32 here using this model. And if I am going ahead with Spearman or Pierce, let me look at going ahead with Spearman correlation to see if there is some kind of an improvement. The Spearman is showing 38, much better than the previous case. And even when I am going with Kendall tau, even that is 27.7. So compared to your original, your first model of Poisson regression tree model, this is looking slightly better because the correlation between the predicted and the actuals in terms of estimating the number of visits to the doctor is slightly better off, and I can very well use this model for the prediction purpose compared to the previous one. So that's how we have to look at modeling the count related data. So these are the things that I wanted to cover as a part of this session. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have given below, or you can send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.